Well, let's get started here. Um, in the last class, we were talking about this idea of an order parameter field, right? That is an order parameter that can change as a function of position. And the first example that I made of something like that was the picture here, right? So this is a non-uniform Ising magnet in a disordered phase, that is for temperature above Tc. And this is in a semi-infinite geometry, meaning that it's infinite in one direction, but it is bounded on the other direction. All right, so here it's infinite over here. This is the bulk where the magnetic order parameter is 0 because the temperature is above Tc. But there's some surface which tends to align the spins so that the magnetic order parameter has to be 1. Um, so there is going to be a magnetic order parameter that depends on position, right? There has to be an m as a function of x. And so one thing that we worked on in the last class was figuring out what's the free energy in terms of this m of x. Right? And so that gets an expression like this. Okay, this is how we ended the class last time. So that the free energy is the system size in the y and z directions times an integral over all possible values of x, starting at x equals 0 at the wall and going up to x is infinity, right, in the bulk. And the thing that gets integrated is the free energy density, that is the free energy per unit volume, which we write down in this Landau style way, where there is a power series. Okay, so there's the 0th order term. There's the 2nd order quadratic term. So some coefficient times m squared. And then there is some gradient term. And for this geometry where m just depends on x, then that term is something proportional to dm dx squared, the derivative squared. Okay, so this now is a free energy which depends on the function m of x. And we want to know what m of x function of all the possible functions gives the lowest possible free energy. Okay, so that's the task for now, right? And so the way we address that is through this same method of variational calculus as I was showing you before. So to do this variational calculus problem, we would say, suppose we want to consider some particular m of x function and see, could it possibly be the minimum? So in order to test that, we will make a little change. We'll change m of x to m of x plus delta m of x, where this delta m of x is a very small change. And then we see what happens to the free energy. Okay, so the old free energy, F, changes to a new free energy, which is F plus delta F. Right? And we look at what are the terms in the change delta F, which are linearly proportional to the change in the function M. Right? So delta F is going to be an integral over all possible values of X of something times delta M of X. And this something is the functional derivative of the free energy with respect to M of X, which we could write like this, df d M of X. Okay, so now we can figure out what is this object, right? What goes here using the same method as we did for the bobsled problem. Right? That is, we plug in this M plus delta M, where there used to be just the M over here. And then we expand all the terms, right? And we write them on 3 lines, like I did before, right? So there's the old free energy, there's the higher order terms that I don't care about, and then in the middle are the terms that are linear in the change. Okay? Now, luckily, this problem is a lot like the bobsled race problem, right? In terms of the way that the free energy depends on M of X, right? It looks like there's a constant plus something proportional to M squared plus something proportional to the derivative squared. That's just like the travel time in the bobsled problem, right? Where there was a constant term and a term proportional to y squared and a term proportional to the derivative of y with respect to x squared. Okay, so we can say it's just like the bobsled race. But now the variable, that the variable y of x, we're now changing it to M of X, and the travel time is now the free energy, okay? But it all works in just the same way. So we can figure out how the calculation goes. We can figure out what is the derivative of f with respect to M of X. So first of all, of course, we have the coefficient out in front, right? Everything is just proportional to that. So that is Ly Lz times something. Okay. Then we have a constant. The derivative of a constant is 0, right? I mean, that's the same as you learned in your first year calculus class, right? So the derivative of a constant with respect to one variable or two variable or partial derivatives with respect to any number of variables, right? Those things are all going to be just 0. Okay. So forget about that. Okay, now we have the quadratic term. So this term just includes the dependence on M in this way, right? It's just proportional to M of X squared. So to take that derivative, we just differentiate in the ordinary way with respect to M. Okay, and so we get A prime t minus tc. So that's the overall coefficient. Well, so there's 1/2 A prime t minus tc is the overall coefficient, times the derivative of m squared, which is 2 m of x. Okay? And then the factor of 1/2 cancels the factor of 2. So this is just like what we had in the bobsled problem. Okay? And then we have the derivative term there. For this derivative term, when we do the substitution, we don't get delta m, we get the derivative of delta m in that term. And so we need to deal with it by integration by parts, the same way that we did before. So we get the same answer. Okay, so we get the same answer and we can just kind of remember how it goes, right? We get a change in sign from positive here to negative because of the minus sign in the integration by parts. And then we get the coefficient of k, and the derivative on delta m moves over to be a second derivative acting on m. So that makes a second derivative of m with respect to x, like that. Okay, so you see, I was skipping steps, right? I was doing steps in my head because these things are just like what we did in excruciating detail for the bobsled race problem. Right? But are there questions? Are you guys good with this, right? With kind of imitating things from one problem to another? Or would you like me to do it in more detail, working out the steps? You're okay? I'm not hearing complaints. All right, well, lacking complaints, I will move forwards then. So what we want to do is to say, the only way that m of x can possibly be the minimum that we seek is if this derivative is equal to 0 for all x. So that gives us a differential equation to solve. Okay, and so now we can see what is the differential equation. Right? It must be that the second derivative of m with respect to x is this a prime t minus tc over k times the function itself. And this coefficient must be positive because t is greater than tc, right? That was one of the assumptions that I made from the beginning of this problem. Okay, now, have any of you ever seen a problem like this, right? Where the second derivative is proportional to the function itself with a positive constant? Yes, I hope so, right? Because this is, again, just like that bobsled race problem. Okay, so it's the same problem, same solution. Okay, so we now can say, let's just call this constant something. Let's call it 1 over psi squared. Right? So that means that psi is the square root of k over a prime t minus tc. Right? So the equation that we're solving is that the second derivative is equal to m over xi squared. And this is some kind of length. Right? We can tell it must have units of length because the units of m are the same on both sides of this equation. And then there are two derivatives with respect to x, right? So there must be a factor of 1 over length squared on this side that better equal a factor of 1 over length squared on that side. So the solution of this, as you remember, is that m of x is equal to 1 constant times e to the x over xi plus another constant times e to the minus x over xi. Okay, and now these two constants have to be determined by the boundary conditions, right? This is a solution to the differential equation for any constants, but we need to match the boundary conditions. So what are the boundary conditions in this problem? Well, if we go back to the original question, we see that we have to have m equals 1 right at x equals 0. Right, that's one boundary. And we must have m equals 0 when x goes to infinity. Okay. So m equals 1 at x equals 0, and m equals 0 as x goes to infinity. Okay, so let's deal with the second boundary condition first. Okay, so the second boundary condition, right? That let's plug in x goes to infinity into our equation for m right here. Okay, so this says that 0 is equal to c1 times, well, the exponential of infinity. That's huge, right? Infinity. Okay, plus c2 times 0. That's 0. Okay, so therefore c1 better be equal to 0. And in that case, we can then plug into the second boundary condition, which tells us that 1 now is equal to 0 plus c2 times e to the 0, which is 1. Okay, so that tells us that c2 is equal to 1. So our solution then is m of x equals e to the minus x over xi. Okay, so this is this is the solution to the particular problem that I made up. Right? And so what this tells us is that if you have a disordered phase, the m is equal to 0 in the bulk, but m might not be 0 near a surface. Okay, so near a surface, you could have a profile for m of x that looks like this, right? It's an exponential decreasing. Okay. And so the surface induces order in some limited size region. And what's the size of this region? Okay, well, that comes from what's the denominator in this exponential, right? That when x goes to psi, m is down by a factor of e compared with the place where it starts, right? So if it starts here, then when you go in a distance of psi, then m gets down to a factor of 1 over e, so about 0.4 of where it started. Right? If you go in a distance of 2 psi, then m is down by a factor of 1 over e squared. Right? So it's down to like 16% of where it started. Psi has an important physical significance. That is, psi tells you how far does this surface-induced order extend into the bulk. Okay. The word for that is a correlation length. So one thing we're learning from this calculation is that if you have a surface that induces some order, that order doesn't stop right away. That order doesn't go on forever, but it goes on for a certain length, this correlation length psi. Now, one other thing that we get from this calculation is how the correlation length depends on temperature. Okay? So look here at this equation, right? It includes temperature in the denominator. When the temperature is really high, the correlation length is really short. Okay, so I could draw that in some other color, in blue. This is some high temperature. Okay? When the temperature is lower, the correlation length is bigger. That is, the order goes farther in to the bulk. Okay? When you get down really close to TC, then this denominator becomes very small. And so that means the surface-induced order goes really far into the bulk. So I could draw that with another color, make that green. Okay, so this is just above TC. T slightly greater than TC, right? So if T is slightly greater than TC, then the surface-induced order goes really, really far into the bulk before it drops down to 0, right? And then, what if you actually go down to TC or even lower, right? Well, if you drop down to TC, then the bulk doesn't have n equals 0 anymore. Okay? At TC, the bulk has some non-zero magnetic order. Or excuse me, right at TC, the bulk is still 0. Lower than TC, the bulk starts to be something non-zero. Okay? And so if T is below TC, then the plot would be something more like that, right? So it never goes to 0. It goes to the bulk magnetic order parameter instead. Okay. So you could see, this is now the temperature evolution for a non-uniform system. Right? That with a non-uniform system, the order might come in from the surface, okay, as you reduce the temperature. The order doesn't just appear everywhere at the same temperature, but it could come in from the surface as you cool, you get more and more order. It's going farther out like that.
Excuse me, can I ask a question?
Please.
When T goes below TC, then we can see the coefficient in the differential equation. Here, ordinary differential equation above becomes negative, right? Then the solution would be a sinusoidal functions. Right?
You caught me. You caught me. I was hoping nobody would notice. This equation is derived with the assumption that T is greater than TC. Okay, and so my solution to the equation only works if T is greater than TC. Right? If T is less than TC, you have to solve a different equation. And I just got so excited about drawing the graphs, I kept on drawing the graphs, even though I haven't actually solved that problem yet. I got ahead of myself, but you caught me. Thank you. All right. I'll get to T less than TC really in just a minute. Okay. So the last thing I should say about T greater than TC is that the dependence of the correlation length on TC, on temperature, excuse me, on T, can be described by another one of these critical exponents. Okay? So we could say there is, whoops, wrong pen. There is a critical exponent that tells us how does the correlation length increase as T approaches TC. Okay? So here we are seeing that the correlation length is proportional to T minus TC to the negative nu power. And so here the prediction of this Landau theory is that nu is equal to 1/2, right? So that it is a square root law. And that's another prediction which is approximate, it's not exact. This prediction can be tested experimentally to see, how good is Landau theory, and to compare with other theories that are much more complicated than this, which include improvements on Landau theory. Okay, so that is the information to extract for T greater than TC. Okay, but now let's come back to Cheng's question, which is, well, what happens if T is less than TC? Okay. So let's say, now let's consider T less than TC. Okay, so this is now a new example. Okay, so it's going to be a different calculation than the one that I just did. Okay. So this is a different and somewhat more complicated calculation, because now the bulk is not going to have n equals 0. Right? The bulk has some non-zero value for the magnetic order parameter. So the bulk might have, so we'll say the bulk M is not equal to 0. Okay? So the bulk might have the spins which are mostly pointing up, with some pointing down. like that. Okay. This is some positive value of M. Or the bulk might have the spins mostly pointing down with a few pointing up. Something like that. Right? This is M less than 0. Okay. So here's a new problem to think about. Suppose you have a system that looks like this in one place, and it looks like this in another place. That's actually a common situation, right? It could well happen in some experiment, right? That if you cool a magnet from the high temperature phase into the low temperature phase, that it develops magnetic order spontaneously. It's randomly going to be up or down. But suppose it's mostly up in some place and it's mostly down in another place. Right? That could happen. In that case, you could ask, what happens in between these regions, right? When you go from one to another, right? You must have that M is changing as a function of X as you go this way, right? So maybe somewhere right in the middle, you have M equals 0 with exactly half pointing up and half pointing down, right? So in this situation, we could guess that there's a plot of M as a function of X that looks something like this. Whoops, well, here I'm going to move the axes. Let's see, let me erase that. Let's make a plot for M as a function of X. And so maybe it's the negative value way over on the left for negative X. And it's this positive value way over on the right. And somehow it has to get from here to here. So there must be some M of X function which might look like that. Or maybe it's smoothed out like this. Or maybe it's kind of sharp like this. Or maybe it's extremely sharp like that. Okay, so this is another problem where we want to say what M of X function gives the lowest free energy. So this is another variational calculus problem. Okay, so in this problem that I'm just suggesting here, there's no wall, right? This is an infinite system, not a semi-infinite system, right? There's no wall, but internally the system is going from one negative value of the order parameter to a positive value. And these two values of the order parameter are the bulk order parameter plus or minus M0 that you calculated in homework number 1. So let's think about how to solve this problem. Okay. So this is another problem where we need to minimize the free energy integral. So once again, the free energy is an integral over all positions. Okay? Now, since nothing depends on y or z, those just give trivial factors for the system size in front of the integral. But then there's an integral over x from one extreme to the other extreme. So that is from minus infinity to infinity. And the thing that needs to be integrated is the Landau free energy density. Okay, so there's this 1/2 a prime t minus tc m of x squared. Okay. Now I have to be a little bit more careful because I can't just neglect the m to the 4th term in this problem, because the order parameter is not so small. I mean, the order parameter might be large in a big region of the sample, over there, okay? So I better not neglect the m to the 4th. I better include it in the theory. So I will write plus 1/4 b0 m of x to the 4th power. And then I need to add the derivative term. 1/2 k dm dx squared. Okay, so now this is a variational calculus problem, which is slightly different from the one that we did before. Right? It's pretty similar, but it's slightly different because we have the m to the 4th term, and also because we have t less than tc, and so this term looks like it did before, but t minus tc is a negative number. Okay, now we want to solve this using the same kind of method that we did before. Right? That is to see if we make a little change in m, what does that do to the free energy? And then to set that change equal to 0. So that'll be the Euler-Lagrange equation. Okay, so we can solve it using, well, we can solve it using approximately the same method that we did before. Okay, so now the functional derivative, that is the change in f in response to a small change in m, we can calculate that from the expression for the free energy. So first, of course, we have this constant term. The derivative of that is 0. Then we have this quadratic term. We already know about that one. Okay? The derivative of that is the same thing that we already derived. Okay, so a prime t minus tc times m. Okay, now we have this new 4th order term that we haven't considered before. But it's actually not that hard. Okay, it's not that hard because it just involves m. It doesn't involve any derivatives of m. So when we make a little change in m and we see how is that change proportional to delta m. That just means we need to know what's the first derivative of this thing with respect to m. There's no dm dx's involved. So the first derivative of that thing is plus b0 m of x cubed. All right. And then we get to the last term, the derivative term, and we've already done that a couple of times. So we still have the same functional derivative. That makes negative k times the second derivative of m with respect to x. Okay, so this then is our functional derivative in this problem. And the only way that m of x can be a minimum of the free energy is if this derivative is equal to 0. So that is our Euler-Lagrange equation for this problem. So once again, I've skipped steps, right? I've tried to jump ahead and do the steps just in my head based on analogies with previous problems. If you have questions about that now, I'm happy to answer them now. If you want to ponder, and you can practice doing it yourselves with writing out the 3 lines as before, you can practice that, and if you have questions, you can ask me later. That's fine. Okay, so now here is an Euler-Lagrange equation to be solved. Okay, and so the differential equation that we need to solve now looks like this. It is that k times this second derivative is equal to a prime t minus tc times m of x plus b0 m of x cubed. And this term is now negative. Okay, now this is a much harder differential equation than the one that we had before, right? It is much harder because it is not linear, right? So you can see, the old differential equation with just this term and this term, right, was a linear differential equation, right? Meaning that everything was at that time just proportional to m itself, okay? This isn't, right? Because this is linear, but this is an m cubed, okay? That spoils the linearity. Okay? In general, most nonlinear differential equations cannot be solved exactly. And so this is a very complicated subject in mathematics, and usually we need to do complicated numerical solutions or approximations. In this case, just by good luck, this equation can be solved exactly. And I don't expect you to just guess that, but I'll tell you the answer. Okay, so the exact, wrong pen. The exact solution is that m of x is equal to m0 times the hyperbolic tangent of x minus x0 over psi, where M0 is the bulk magnetization that comes from minimizing the bulk free energy that you already know about. Okay, and so this is the square root of A prime TC minus T over B0. Okay. So this is something that you already know about. Okay. This hyperbolic tangent function, this is also the function that you already know about. We've talked about it in other contexts. Here it is just showing up once again. And here the psi in the denominator is a correlation length, which is defined similarly to what we had before, but not exactly. It's now 2k over A prime TC minus T. Okay, so one difference from what we had before is that there's a factor of 2. And the other difference is that it's TC minus T. So this is a positive number inside the square root. Okay, so it's the square root is something real. Okay. And x0 could be anything. If you want to check if I'm making a mistake or not, right, one thing that you could do is to plug this into the differential equation, right? I mean, you can take this expression and plug it into the differential equation up there and use what you know about second derivatives of the hyperbolic tangent, or else get Mathematica or other software to do it. Right? And then you have to use some trig identities for hyperbolic tangents over on the right side. But it works. Okay, so try it out on your own and you can check that it works. So the importance then is, what does this function look like? Okay, so if we make a plot of that, we get a plot like this. Okay, so for m as a function of x, the hyperbolic tangent looks like this, that it is negative and then it curves around and becomes positive. Okay? And so M0 tells you the range that it goes through, right? That the hyperbolic tangent is changing from negative M0 up to positive M0. Okay? And then the parameter psi tells you the characteristic width of this change. So the change happens over a certain range of x. Okay? That's not to say 100% of the change happens over that range of x, but most of the change happens over that range of x. There is some characteristic length scale that says, you know, is the range from here to here, is that nanometers or microns or centimeters or what is it, right? And so once again, psi is a correlation length. And once again, it depends on temperature. Once again, it is proportional to now Tc minus T to the nu power, where nu is equal to 1/2. So this is on the low temperature side of the transition. You get now this temperature dependence. And then there's the parameter x0, which goes into the equation, right? And it could be anything. And that parameter says, where is the position of the wall? Okay, so that is right up in here, okay? This is the position x0. So one good way to think about this whole solution, right, is as a wall or an interface between two phases. Okay? So over here, we have the spin up phase. Over here, it's the spin down phase. Those two phases have some equal free energies. Okay. Now, if you have some region of your sample that is in the spin up phase and another region is in the spin down phase, then there will be a wall in between them. This is a model for the wall. Right? This whole thing in here, make another color, right? This whole thing in here is what we might call the wall or the interface between the two phases. There is also a fancy word for this kind of a solution, which you can use to impress your friends. This is called a soliton, right? A soliton is a mathematical term to mean this kind of solution to a differential equation, which has a characteristic amplitude from there to there, and a characteristic width from there to there. Right? And so this is a solution which it can't just get bigger or smaller. There's no superposition principle. And it can't just spread out, right? But it has a characteristic amplitude and width. Okay? And so this is showing us that the wall or interface or soliton or surface, and be another good word, surface between two phases, that it has an amplitude, a difference in the magnetic order parameter, and it also has a certain width, right? You don't have just one phase and then boom, that's the end, and there's the other phase. Instead, there's some transition region where you go from one phase to the other phase. And the correlation length tells us about what is the width of the transition region. There's one more thing that you can get from doing this calculation, which I will just mention briefly because I'm getting a little over time. Okay, the thing that you can get from this is you can also take this solution and plug it back into the free energy. Okay. So here is the free energy for any function m of x. Okay. Now that we have solved for what is the optimum m of x, and we have this expression right there, okay? So we can plug it into the free energy. And by doing that, we get what is the minimum free energy? What is the lowest possible free energy? Now we can compare that with what would be the free energy if we just had a uniform phase everywhere. Right? So we could then compare with the F uniform. What would it be if we didn't have any interface? What if we just had spin up everywhere? Or what if we just had spin down everywhere? Right? The free energy that we get, this minimum, compared with F uniform, it's not the same, okay? So there is some delta F, which is the minimum free energy minus F uniform. And there's an exact calculation which gives this, and I don't have time to do the messy integral, but what we get is it's some Ly times Lz, right, times the result of a complicated integral. Okay? There's an interesting physical interpretation of this, right? The thing that comes from doing that complicated integral is, how much is the excess free energy of the interface divided by the area of the interface. Okay, so this is the excess free energy per area. And the word for that is surface tension, right? Between the two phases, right? It is excess free energy per area. Okay. So what we have made through this method is a model for the surface tension between the spin up phase and the spin down phase in this magnet, okay? And in the text, I worked out that this surface tension, it usually gets the letter sigma, and it is 2 to the 3 halves times k to the half a prime to the 3 halves tc minus t to the 3 halves, all divided by 3 b naught. Okay. And the thing to notice about this, once again, is the temperature dependence right there. Okay. So you can see that if we are close to the critical temperature, the surface tension goes to 0. Because right at the critical temperature, there's no more difference between the spin up phase and the spin down phase, right? Those two things become equivalent. So no energy associated with the surface. But when you reduce the temperature, the spin up phase and the spin down phase become more different from each other. And so the surface tension increases following this Tc minus T to the 3 halves power. Okay, I'm over time. I better stop here. So I will I will be glad to answer any questions about this or any questions about the homework that you're working on. And then have a good weekend, except for the homework. And I'll see you guys on Monday.